Hello, my dear students. Welcome to my class of Astrophysics. Today's topic is energy, kinetic energy, and work energy theorem. First of all, what is energy? Energy of a body is defined as the capacity or ability of the body to do work, and it is measured by the amount of work that the body can perform. It is a scalar quantity, just like work. Because the kinetic energy, it is measured by the total work done. Any energy that is measured by the work done. One object possesses some energy means it has capacity to do some work. It is a scalar quantity. Let us know some basic facts about this energy. SI unit of energy is the joule. That is same as the energy of same as the unit of the work. And CGS unit is arg. Dimensional formula energy is the mL2 T minus 2, same as that of work. So all things, energy and work both possess same unit, both have the same unit, same dimensional formula. Practically, always energy is measured by the work done. Some other units which are used in the different places, and as far as example, electron volt in atomic level, subatomic particles level, the energy unit of energy, that is the electron volt, is considered. And 1 electron volt, it is a very small amount of energy, and that is equal to 1.6 into 10 to the minus 19 joule. Mega or million electron volt, MeV, that means 10 to the power 6 electron volt, and when we multiply it by 10 to the power 6, it is the 1.6 into 10 to the minus 13 joule. Another kilowatt hour, it is another commercial unit, that is 3.6 into 10 to the 6 joule. 1 calorie, basically this unit is used for the heat energy, and 1 calorie that is equal to approximately 4.2 joule. And the relationship between arg and joule, arg, it is a very small unit, and 10 to the 7 arg is the 1 joule. That means 1 arg is equal to 10 to the minus 7 joule. These are the different units used at the different places. Now, characteristics of energy. There are some basic characteristics of energy. Now, number one, the entire matter possesses energy. Entire matter possesses energy. Number two, energy can neither be created nor be destroyed, but it can be transferred from one form of energy to other. That means in our daily life, we cannot create or destroy energy, and the energy consumption means the energy convert from one form of energy into another form of energy, but in such a case it is not that destroyed. Let us suppose the electrical energy is consumed here, but that convert into other form of energy, but it is not so that it is destroyed. Number three, energy can be stored and it can be transferred to other matter. That means one object possesses some amount of energy, it can be stored within that object, and that can be transferred to other object also. Total energy of universe is always constant, and energy transferred or transformed can be measured. How much amount of energy can transfer from one object to another object, or transform from one form of energy to other form of energy, that can be measured. That means energy can be stored, can be measured, can be transferred. These are the basic characteristics of the energy. And in any ordinary process, energy is neither be created nor destroyed. Total amount of energy in the universe from the beginning, that remains unchanged till now. Now, different form of energy. Energy is of several forms: mechanical energy, heat energy, sound energy, light energy, electrical energy, nuclear energy, atomic energy, chemical energy, magnetic energy, etc., etc. But in these topics, here in your standard, basically here we considering mechanical energy in this chapter, in these topics. There are two types of mechanical energy. Mechanical energy means energy is produced by mechanical means. It is of two types: kinetic energy and potential energy. So what is the meaning of the kinetic energy, or what do you mean by the kinetic energy? What is the definition of the kinetic energy? The energy possessed by a body of virtue of its motion is called as kinetic energy. That means any object or any particle is in motion, and it possesses some kinds of energy due to the motion, that is the kinetic energy. Quantitatively, the kinetic energy is equal to work done in bringing the body moving with speed v to rest, or alternatively, it is also equal to the work done to make the body to move with speed v starting from rest. In the two way we can measure the kinetic energy. That means, let us suppose one object is in motion, it possesses some kinetic energy due to its velocity v. Then at that time that object capable to do work, and what is the total work done by that object to comes to rest, and that is the measurement of kinetic energy at that moment for that object. Otherwise, let us suppose the object initially it was at rest, and some work is done on this object, and it gains a velocity, and to get that velocity, what is the amount of work done during that process, that is converted into kinetic energy, and that is also the measurement of kinetic energy. Now, in this way, we can find out the formula for the kinetic energy. That means expression for the kinetic energy. That means we can measure the kinetic energy at all. Kinetic energy of a body can be calculated by number one, the amount of work done required to bring the body into motion, its state of rest. That means initially, let us suppose the object is was at rest, and now it is in motion. Then what is the amount of work done or required to bring the object into motion from the state of rest? Otherwise, the amount of work done in stopping the body. That means object already in motion and it possesses some kinetic energy. And what is the amount of energy spent to stop the object, or during the stopping process, what is the work done by that object? That is also another way to measure or to find out the expression for the kinetic energy. Here we generally using the first method. That means initially object at rest. Let us suppose a body of mass m initially at rest. Let us say a force F is applied on the body such that the body gets displaced by ds vector along the direction of the applied force. Then what is the dw for the very small displacement? We can write dw is equal to f dot ds, that is f ds cos of 0 degree, because we are considering the displacement taken place along the direction of the applied force. Then f into ds, that is the dw, very small displacement along the same direction of the applied force. Now, according to Newton's second law of motion, we know f is equal to m into a, and m into dv dt. A means rate of change of velocity, that is dv dt. Therefore, we can write dw is equal to f into ds. F means we can, in place of f, we can write m into dv dt, that is mass into acceleration from the second law, and into ds, that means it is for the work into ds. And now if we write in this way, this expression m into dv or into ds by dt, and ds by dt is nothing but the velocity v. Now dw we can express in terms of velocity. Mass is the constant. We are taking the mass of the object throughout the whole process is remains constant. M is constant. Now the work dw, very small work done in terms of v, that is the v into dv. How can we find out here? Again, I am telling here dw is the f dot ds, that is the f ds, because cos in the same direction cos 0 is the 1. And from the Newton's second law, if we put the value f, that is the m dv dt, m into a, that is m dv dt, and now written in this way dv into ds by dt, and ds by dt is nothing but the v. So dw is equal to m into v into dv. Therefore, total work done to increase the velocity of the body from 0 to v is given by. Now we can find out the total work done by the calculus method. Already we know this. First of all, we have to find out the very small work done dw. Then we have to take integration by taking proper limit. In this case, already initially we are taking that object was at rest. That means initial velocity is a u is a 0, and the final velocity is a v. The m v dv, that is m, if we, it is a constant, it is outside of this integration, and the integration 0 to v, that is v dv, and v dv, that power 1, that is v square by 2, 1 plus 1 divided by 1 plus 1, v dv, the integration of v dv is the v square by 2, and limit is 0 to v. because we are using this formula x to the power n dx is the x to the power n plus 1 divided by n plus 1. Now by putting the upper limit minus lower limit in this way, W is equal to m into v square by 2 minus 0 square by 2, that is the mv square by 2 or half mv square. Therefore, work done to bring the object from rest to motion at the velocity v, so that is the half m into v square, and there is work done and appears in the form of kinetic energy of the body, and therefore we can write the kinetic energy, that is half mv square, and it is a very well known formula, already you know it, half mv square. And how can we find out it? It is the one process, one way we can find out the expression for the kinetic energy. In this case, we are taking in the amount of work done required to bring the body motion from its state of rest. In this way, in this process, we are calculating the total work done, and that is nothing but the half mv square, and that is nothing but the kinetic energy. Obviously, the dimensional formula for the kinetic energy for the same as dimensional formula of the energy, any energy, also the dimensional formula for the work done, ml2 t minus 2. Then unit, obviously, unit of all types of energy are same in SI system, that is the joule. Now, work energy theorem. It is another very important concept related to the kinetic energy. Obviously, in this theorem state that the work done by the external force acting on the body is equal to change in kinetic energy of the body. That means work done is nothing but the change in the kinetic energy. Change means, let us say initially it has some amount of kinetic energy, and some work is done by any external force, and it gains some kinetic energy, and there is a change in the kinetic energy. This change in the kinetic energy, work done equal to the work done. It is known as the work energy theorem, and we can easily prove it. Let us consider a body, and let us consider a body of mass m, initially moving with velocity u. Let us say constant force F act on the body. Initially, we are taking a constant force. We can also find out the same expression for any variable force also. In all cases, the work done, that is equal to the change in kinetic energy. Let us suppose in first cases, considering the constant force F on the body, such that acceleration A is produced in the body on covering a displacement s, the velocity of body becomes v, and then using the equation, initial velocity it was u, and after the applying force there is displacement in the same directions. That means there also, since there is a force, there is also an acceleration a, and we know from this equation v square minus e square equal to 2as. That means acceleration in this process, that is v square minus e square divided by 2s, where s is the displacement. That means initial velocity u, final velocity v, displacement s in the same direction of applied force. And since there is a force, therefore there will be an acceleration. And what is the acceleration? A is the v square minus e square divided by 2s. Now work done by the external force in displacing body, that we know that is W is equal to F dot S, or Fs cos of 0 degree, that is F into S. And from the Newton's second law, we know F is equal to m into A. Therefore, W is equal to m into A into S. We can write here because we are considering the force throughout the whole process, that is remains constant force. Therefore, W is equal to m into A into S. Now, what is the value of the A? In from the equations of motion as uniform accelerated motion, we can write here A is equal to v square minus u square by 2s. We can take here uniform because we are considering the force constant for the whole process. Now putting the value of A, W is equal to F into S, that is m into A into S. Taking the value of A from the above equation, and W is equal to m into v square minus u square divided by 2s into S, or m s cancel out, m v square minus u square by 2, and that is nothing but the half m v square minus half m u square, and it is nothing but the kinetic energy final, and it is the kinetic energy initial. Kinetic energy final minus kinetic energy initial, it is nothing but the change in the kinetic energy. Therefore, it is now proved because we know the formula for kinetic energy now, half m v square, half m u square. It is the kinetic energy, final kinetic energy, it is the initial kinetic energy, and how we obtain from the work done. From the work done by this force, the work done is now this, and that is nothing but a kinetic energy change Therefore, work done by the external force equal to change the kinetic energy body, which is work energy theorem. It is now proved. It is now proved now. The changing the kinetic energy is equal to work done. Work energy theorem for variable forces. If we consider the force is not constant, if we not constant, then we cannot put the value this one v square minus c square by 2s. You can only put the value when the force is constant. That is mass a is constant. Otherwise, in case of variable force, we can also find out the similar way, and you get the same answer. Same answer means the work done that will be changed the kinetic energy. In this case, let us suppose mass m of the body moving along x-axis, and ax is the acceleration at any instant due to force F at that moment. Therefore, the work done W by the variable force F on the body in displacing body from initial positions to final position is given by. In this type of case, already we have discussed here the work done by a variable force. We have to take very small displacement, and then we have to take integration by using lower limit and upper limit. Very at any place, let us suppose fx is the force. Fx means it is function of the x. That means f is variable, and for the very small displacement dx, the work done dw, that is fx dx, and by taking the integration xi to xf, that means initial position to final positions. Now we can write it if that is the m into x. X is also function of x. It is not a into x, it is x. X, that is a suffix, and that is the acceleration along the x-axis. Since the force along the x-axis, therefore we write here. And now ax we can write in another way. Ax, there is a v d vx dt, there is rate of change of vx with respect to time. And now we can write it is the dvx dx. We can multiply both numerator and denominator dx, and now that is the dv by dx. Here dv by dx into dx by dt, and dx by dt nothing the vx. So dvx by dx into vx, since vx is the dx dt. Now ax, we can, in place of ax, we can write it is a vx dvx dx, because v is also variable function of x, and dx in this way. Ax, it can be written in this way, both are same, but it is in the term of the vx. Putting the value of the ax in equation 2, this equation, if we put the value of ax and changing the limit. So really, when we take the variable va, then we have to take the limit of the v in place of the limit of the x. And let us consider the initial velocity at the initial position, that is the vi. I means initial, and at the final position it is the vf. So m into vx dx whole into dx. Now putting this value here, dx is cancel out. Now it is totally the function of only v, that is it is the only variable with the v. Now we can perform the integration. Here there are two variables here. Here there are two variables, one t, another dx. Therefore, we cannot solve this problem, and gradually in this way we convert the total variables in the terms of velocity variables, initial velocity vi, final velocity vf. So m into vx dvx dx whole into dx. Now vi to vf, m into vx dvx, and we know the v dv, the integration of v dv is nothing but the v square by 2. In this case, we are writing this vx in place of vx. You can also write v also, and lower limit u and v also you write. Here we are writing another way. It's also okay, and if you write u and v, that's also okay. In place of vx, you can write v, that is also okay. But here we are considering the motion is along the x-axis, therefore we are using suffixes x in all term, variable term, and vx dvx, and the integration vx dvx is nothing but the vx square by 2, that is vi by vf. And by putting the upper limit minus lower limit, we get this half m into vf square minus half m into v I square. it is nothing but the final kinetic energy minus initial kinetic energy. Again, it is proved that the change the kinetic energy is nothing but the work done during the process. You may prove in this way when the force is variable one, otherwise when the force is constant one. You can also find out the change the kinetic energy by the law of equation of motion, and from the second law here also by integration method with the help of second law we can prove that the change the kinetic energy that law is equal to the work done. Now another basic concept relation between kinetic energy and momentum of an object. A moving object possesses both kinetic energy and momentum. Both are the property of only when object in motion, but they both are also related to each other. How they are related, how their values related. Kinetic energy, it is scalar quantity, momentum obviously it is a vector quantity, but when we correlate them, we are only using their values, numerical values or magnitudes. We know kinetic energy half mv square, and linear momentum, that is the mv. At any moment we can use this mv. Even momentum, it is a vector quantity. At any moment, particular moment, at that time, the velocity is the v, momentum is the m into v. Now k, kinetic energy, that is the half into m into v square. That can be written in this way. We can multiply both the numerator and denominator by the m. Therefore, it is the m v whole square divided by 2m, and it is nothing but the pp, the momentum, linear momentum, that is p square by 2m. Therefore, k equal to p square divided by 2m, or p square equal to 2mk, that is p equal to root over 2mk. K is the kinetic energy, p is the momentum. It is a very well known relationship between the kinetic energy and the momentum. It is used in several places, different places, in physics, in chemistry, to solve the problems in different places. And there is very important one relationship between the kinetic energy and momentum. Both are the properties of moving object. When any object is in motion, both they possess kinetic energy and momentum, and it is the relationship between the kinetic energy and momentum. Naturally, kinetic energy when increases, momentum also increases, but the relationship is p varies root over k, not directly proportional. Now, discussion of the work energy theorem. According to work energy theorem, we know W is equal to half mv square minus half mu square. That is final kinetic energy minus initial kinetic energy. Case number one. If there is no change in the speed of the body, then the work done by the force is zero. We can say when from the concept of the energy, kinetic energy, work energy theorem, since there is no change the speed, therefore there is no change the kinetic energy, and we know that W is equal to half mv square minus half mu square. If v is equal to u, the force is acting, but there is no change in the speed, there is no change in the kinetic energy. At that case, we can definitely say work done is zero. Therefore, kinetic energy of a body depend only on the speed, not on the velocity of the body. For example, in a uniform circular motion, the speed of the body remains constant, but the velocity changes continuously. So the kinetic energy of body having uniform circular motion remains constant. That means kinetic energy, it is a scalar quantity, and it is only related to the speed, not related to the velocity, because in this example, when any object is moving in a circular path, the velocity always changes due to the change in the directions, but when it is uniform circular motion, speed remains unchanged, and therefore kinetic energy also remains unchanged. And here another things we can say, that when speed remains constant, therefore work done is zero. That means in circular motion, the force, centripetal force, work done zero, we can say from this concept. Now, case number two, if there is increase in the speed of the body, then work done by the force is positive. Obviously, when increase in the kinetic energy, the work done by the positive, and that means change in the kinetic energy is positive. When drop body drops certain height, the work done by the gravitational force is positive. As the body falls, speed increases and kinetic energy also increases. That means in any cases when the change in the kinetic energy is positive, kinetic energy always positive, but change the kinetic energy may be positive, may be negative. When the change the kinetic energy positive, at that time work done by the applied force, we can say that is positive work done. From this work energy theorem, we can also say definitely. Case number three, if there is a decrease in the speed of body, then work done by force is negative. Here, obviously, if the final kinetic energy is less than the initial kinetic energy, then the difference is the negative difference. I am saying again, kinetic energy always positive, but difference of the kinetic energy may be positive, may be negative, may be zero. And here, when the change the kinetic energy is the negative, the work done also negative. For example, when a body raised in upward directions from the surface of Earth, then work done by the gravitational force is negative. As the body moves up, its speed decreases, hence kinetic energy also decreases. That means when if you throw any object vertically upwards, and during that motion we observe that kinetic energy gradually decreases. Therefore, the change the kinetic energy is negative kinetic energy here. Therefore, work done by the gravitational force obviously negative work done. Since the speed and mass of the body are positive physical quantities. So kinetic energy of body is a positive quantity, but change of kinetic energy may be positive or negative. While providing the work energy theorem, it is assumed that the work done by the force is effective only in changing the kinetic energy of body. However, the work done on a body may also stored as potential energy of the body. That means in all the derivations, in all cases, above the cases, when we prove the work energy theorem, we have to say that there is no change of the amount of work to other form of energy rather than the kinetic energy of in different cases when were done some amount of work done convert into potential energy and some convert into the kinetic energy. At that time you can definitely cannot say that change the kinetic energy that were done. So when we prove it or when we consider the work energy theorem, we have to always consider at that time there is no change of any amount of work into other form of energy rather than kinetic energy. Now it is the end of this lesson, and we will meet next with next topics in the next class.